You are likely building, or at least heavily preparing, to build AI agents to write software.
Yeah, everybody is right now.
Right. And if you're listening to this, you've probably already run into the primary bottleneck.
Which is almost never what people think it is when they start.
Exactly. It isn't the model's intelligence. It's the sheer velocity of the output.
Yeah.
What happens when your agents generate code faster than your senior engineers can actually review it? Like, how do you prevent your entire code base from just collapsing under the weight of generated AI slop?
It's a massive problem.
Welcome to the deep dive.
Yeah.
Today, we are unpacking the Dark Horse PRD.
It's such a good document.
It really is. For those who haven't read it, this is essentially a masterclass document detailing the blueprint for building a harness-first operating model. And the goal here is creating level 5 dark factors.
And before we go further, let's actually define that term. Because level 5 dark factory, it sounds like something out of a cyberpunk novel.
It really does.
But it's a very specific manufacturing concept adapted for software. So in traditional manufacturing, a dark factory is a production facility that is so fully automated you can literally turn the lights off.
Because there are no humans on the floor.
Exactly, no humans on the floor. And level 5 autonomy, which is borrowed from the self-driving car world, means the system handles all edge cases without requiring human intervention.
Right.
So in software engineering, a level 5 dark factory means you have an AI native environment where human engineers are no longer writing the code line by line.
They're entirely removed from the syntax level.
Right. Instead, humans are designing the environment, setting the governance policies, and writing the evaluation harnesses. The AI operates within that dark factory entirely autonomously, from issue creation to production deployment.
Okay, let's unpack this. We need to be upfront with you about what we absolutely won't do today.
No tool hype.
Zero tool hype. We are completely avoiding it. If you came here for a debate comparing the syntax of LangGraph versus NAN, or, Mastra versus pedantic AI,
This isn't that deep dive.
this isn't it. In the model we are discussing today, frameworks are just transient, replaceable adapters. The tools are going to change 6 months from now anyway.
Oh, absolutely. They change weekly.
So instead, we are focusing purely on the immutable physics of AI software factories. We're talking about harnesses, contracts, evidence bundles, governance, the foundational stuff that actually matters. So to kick this off, what does it actually mean to build a harness-first AI software factory?
To really understand this paradigm shift, we have to look at this fascinating experiment conducted by OpenAI's engineering team.
Yeah, this is wild.
Over a 5-month period, they decided to build and ship an internal beta of a software product. And this wasn't a toy app. It had daily active users, alpha testers, the whole 9 yards.
Real traffic.
Real traffic. But the catch was the constraint they placed on themselves. They built it with exactly 0 lines of manually written code.
0.
Every single line. The core application logic, the testing suites, the CI configuration, the documentation, the observability stack, the deployment tooling, all of it was written by Codex.
And I remember reading this case study. They estimated that this zero human code approach allowed them to build the product in about 1/10 of the time it would have normally taken a traditional engineering pod.
Yeah, a massive speed up.
But the massive realization they had wasn't just, wow, the AI model is incredibly capable at writing syntax. The real epiphany was that their primary job as software engineers had completely changed. They had to fundamentally rewire how they thought about their daily work.
Exactly. The human engineers were no longer acting as the typists translating business logic into Python or TypeScript. They were steering, the agents were executing.
Right.
But the path to get to that 1/10 development time wasn't entirely smooth. In fact, at first their progress was actually much slower than they expected.
Which makes sense.
And it wasn't because the Codex model lacked the reasoning capability or the coding knowledge. It was because the environment it was working in was underspecified. The agents simply didn't have the tools, the abstractions, or the internal structure required to actually make progress toward high-level goals.
Right. It's like putting a brilliant senior engineer in a windowless room with no access to the internet, no ability to run the code they just wrote, and asking them to build a distributed system.
Yeah, they're going to fail.
They're going to fail.
Yeah.
Which brings us to the core definition of the harness. The harness isn't just a simple test script. The harness is the total execution and verification environment around an agentic task.
Total being the key word.
Right. It includes the task state, the tools, the permissions, the observability stack, the evaluators, the data fixtures, the replay capability, and the governance hooks. It is the control plane.
And relying purely on prompting a model is fragile.
So fragile.
You can tweak a system prompt all day, but if the agent can't verify its own work, you're just generating confident guesses. The harness-first model treats the environment as the ultimate judge.
Which means the bottleneck in AI-driven development isn't the generator's ability to write a Python script. It's the environment's lack of specification. If the environment can't evaluate, constrain, and govern the code changes, the agent is flying blind.
And that changes the day-to-day reality of the engineering team. OpenAI described how humans have to stop writing line-by-line code and move up the stack.
You spend your time specifying intent.
Right, specifying intent, shaping the environment, encoding architecture, designing feedback loops. During their zero-code experiment, when something failed, the fix was almost never to go into the prompt and tell the agent to try harder or be more careful.
Yeah, that's a classic beginner mistake in agentic development.
Yeah.
Just telling the AI, double-check your work.
It doesn't work. Instead, the engineers had to step back and ask what capability is missing in the environment and how do we make it legible and enforceable for the agent.
I want to dig into that term, legible. Because if I'm a staff engineer, I'm used to dealing with legibility for humans. I write clear documentation, I make sure my Grafana dashboards are readable. But what does application legibility mean for an AI agent?
That's a great distinction.
Because an agent can't just casually glance at a second monitor to see a spike in a Datadog graph.
What's fascinating here is how OpenAI solved that exact problem. They found that agents couldn't work effectively until the application UI, the logs, and the metrics were exposed natively to the agent as queryable endpoints. Natively. From the agent's point of view, anything it can't access in context while running effectively does not exist.
It's just invisible.
Completely invisible. If a human engineer has to copy-paste an error log from their terminal into the chat window for the agent, the harness has completely failed. That is a manual, human-in-the-loop crutch.
And the technical implementation of making that legible is really clever. They didn't just tell the AI to imagine the UI. They wired the Krung DevTools protocol directly into the agent runtime.
Which is brilliant.
It is. They created specific executable skills for the agent to work with DOM snapshots, take headless screenshots, and navigate the UI programmatically. This meant the agent could autonomously reproduce bugs, validate UI fixes, and actually reason about the browser behavior directly.
And they did the exact same thing for the observability tooling. They made it so Codex could directly query logs using LogQL and metrics using PromQL.
So the agent is its own SRE.
Essentially, yes. Once the agent had that context natively available via its tool calls, you could give it a prompt like, ensure service startup completes in under 800 milliseconds.
Because it can read the metrics itself.
Exactly. It could write a change, deploy it to a local test harness, query PromQL to see the new startup time, realize it was at 950 milliseconds, and then iterate on its own code until it hit the target. It closes the loop autonomously.
That is a massive paradigm shift. If we think about how we onboard human engineers, Anthropic uses a great analogy for this. Imagine a massive software project staffed by engineers working in shifts. But there's a catch. Every time a new engineer arrives for their shift, they have complete amnesia.
Total amnesia.
They have no memory of what happened on the previous shift, no memory of the decisions made yesterday, no memory of why a certain architecture was chosen.
Because context windows are fundamentally limited.
Right. And because most complex enterprise projects cannot be completed within a single context window session, agents are exactly like those amnesiac engineers. They need a perfectly legible environment to bridge the gap between sessions. They need to be able to look around, read the metrics, read the logs, and instantly understand the current state of the application.
And that need for a stable, standardized environment sets up the Dark Horse Runtime Capability Contract, or DHRCC.
DHRCC.
The PRD makes it a constitutional principle that agent frameworks are merely replaceable adapters.
Right.
Whether you are using Mastra for a TypeScript-first environment or Pydantic AI for Python, LangGraph for durable stateful graphs, NN for workflow execution, these are just transient tools that plug into your overarching harness. The harness is the permanent fixture of your factory.
The DHRCC essentially dictates that any framework you adopt must support structured state exchange, trace emission, tool call auditability, granular permission controls, and durable task state.
It's a high bar.
Very high. If a shiny new framework drops tomorrow on Hacker News and it can't meet those basic harness requirements, it doesn't matter how hyped it is. It cannot be used in a level 5 dark factory. It forces a discipline where you aren't outsourcing your architecture to a vendor's abstraction. You own the control plane. You own the harness. The framework just translates your intent into LLM API calls.
But this reliance on the environment brings up a critical challenge.
Okay.
If the agent arrives for its shift with amnesia, and it relies entirely on the environment to get its bearings, how exactly does the environment store that historical and architectural information? If the agent can only see what is exposed to it, where does the actual knowledge of the engineering organization live?
Right. If the harness is the judge and the agent is just the worker on a temporary shift, where does the agent store its knowledge between these shifts?
Exactly.
That brings us to our second major pillar, how we handle memory. And the mantra here is incredibly strict. The repo is the memory.
It is a fundamental mindset shift for human engineers. Think about how much of your company's architecture lives in tribal knowledge.
Oh, most of it.
It's a quick discussion in a Slack thread, it's an ephemeral Zoom call, it's a Google Doc that hasn't been updated in 6 months and that only product managers look at.
The dreaded stale wiki.
Yeah. In an AI native factory, these things essentially do not exist. As far as the agent is concerned, if the decision, the context, or the rule is not explicitly committed into the repository, it never happened. The repository has to become the absolute sole system of record.
But practically speaking, when teams first realize this, their immediate instinct is to just dump everything into the repo. I've seen this happen. A team will create a massive agent.md file in the root directory and just start stuffing every single instruction, architectural rule, and piece of context into it.
It's a disaster.
It is. Always use this linter. Never use this database for this service. Remember to format timestamps this way. The Dark Horse PRD and OpenAI both point out that this is a spectacular failure mode. Making a 1,000-page instruction manual leads to massive context crowding.
It crowds out the actual task.
Right. It crowds out the task, the code, and the relevant docs in the context window. The agent either misses key constraints entirely because they get buried in the middle of the prompt, or it starts hyper-optimizing for the wrong constraints.
It's the attention is all you need problem inverted. When everything is presented to the model as critically important, nothing is.
Exactly.
Agents end up pattern matching locally instead of navigating the codebase intentionally. And there is a secondary, very human problem here. A monolithic manual rots almost instantly. You write a 1,000-line agents.md file, and 3 days later it turns into a graveyard of stale rule.
Because nobody wants to read it.
Agents can't tell what's still true. Humans stop maintaining it because it's exhausting to read, and the file quietly becomes an attractive nuisance that actively misguides the AI. Plus, it's incredibly hard to verify programmatically. You can't run a CI linter to check if a single massive blob of unstructured markdown has crosslinks that actually resolve or if its ownership is clear.
So the solution here is shifting from prompt engineering to context engineering.
Right.
Anthropic defines context engineering as finding the absolute smallest possible set of high-signal tokens to guide the agent. It's about optimizing the utility of those tokens against the inherent constraints of the LLM to consistently achieve a desired outcome. For the repository, this means practicing progressive disclosure.
Progressive disclosure is brilliant, and it mirrors how human file systems were designed in the first place. Instead of treating your agents.md file as the encyclopedia containing all human knowledge, you treat it as the table of contents.
It's just a map.
It's just a map. The actual knowledge base of the repository lives in a structured, modular docs directory. The short agents.md file, maybe keeping it to strictly 100 lines, is injected into the agent's initial context. Its primary job is to point the agent to deeper sources of truth elsewhere in the codebase.
Let's walk through what that actually looks like. The agent starts with a small, stable entry point. It reads the agent.md map, and it says, okay, I'm working on the authentication service. The map tells me to go read docsarchitecture.md.
Right.
It fetches that specific file autonomously. It is taught where to look next, rather than being overwhelmed up front. We don't memorize entire corpuses of information as humans. We use external organization systems to retrieve what we need when we need it.
And the very structure of your repository acts as high-signal context. If an agent is working in a file system, just seeing a file named testodals.py inside a tests folder implies a completely different purpose than a file with the exact same name located in Circore Logic.
Context is everything.
Hierarchies, naming conventions, timestamps, these aren't just for human organization anymore. They provide vital signals to the agent. The agent can assemble its understanding layer by layer, progressively disclosing the complexity only when it's relevant to the immediate task.
Okay, so progressive disclosure solves the where is the information problem. But how do we document the why? How does the agent understand the historical reasoning behind the code? Because if an agent sees a weird, convoluted database query, its first instinct is going to be to refactor it.
Of course.
But maybe that query was written that way specifically to bypass a known bug in an older version of PostgreSQL. If the agent doesn't know that, it fixes the query and breaks production.
This is where lightweight architecture decision records, or ADRs, transition from being a nice-to-have to an absolute necessity. Martin Fowler and ThoughtWorks have been advocating for ADRs for years in the context of evolutionary architecture. An ADR captures an important architectural decision, along with its context and its consequences. In a human team, ADRs prevent you from having the same argument about which logging framework to use every 6 months. In an AI factory, ADRs act as the localized memory of the organization.
In the Dark Horse PRD, ADRs are not just documentation. They are a mandatory governance primitive. They convert architecture from verbal folklore into machine-readable memory. A standard ADR must track the context, the decision, the consequences, and the references. And crucially, accepted ADRs are immutable.
That's the key.
If you want to change the architecture, say you're migrating from Redis to Kafka, you don't go back and do a stealth edit on an old Markdown file from a few years ago. You write a new, superseding ADR that explicitly deprecates the old one.
This gives the agent a complete, traversable historical log of why the system is shaped the way it is. If the agent is trying to optimize a workflow and wants to pull in a random new concurrency library it saw in its training data, it searches the docs, hits the ADRs, and the ADR tells it, no, we decided in ADR 000 DOL to use our own internal map with concurrency helper because it natively integrates with our OpenTelemetry setup.
And it listens.
The agent reads that constraint, abandons the new library, and uses the internal helper. The memory constrained the behavior successfully.
But here's where it gets really interesting. This need for memory isn't just about long-term architectural decisions. It extends to the agent's active minute-by-minute execution state as well. We mentioned the amnesia problem, the agent resetting its context window. To solve this during long-horizon tasks, Anthropic developed a technique called structured note-taking.
I love this technique.
This is essentially agentic memory, where the agent regularly writes notes persisted to a memory store outside of its active context window, usually just dropping it into a file like claude-progress.txt or a notes.md file in the repo.
The example Anthropic provided to illustrate this is just phenomenal. They had Claude playing the original Pokemon games.
Pokemon Red, I think.
Yeah. They didn't prompt it with any specific complex memory architecture. But because the agent was given the ability to read and write to a text file, it autonomously developed its own system for managing its state. It developed maps of explored regions, it remembered which key achievements it had unlocked, and it maintained strategic notes of combat strategies that worked best against different opponent types.
I want to dig into how wild that is.
Yeah.
Because it tracked precise tallies across thousands of game steps. It was writing down things in its notes like, for the last 1,234 steps I've been training my Pokemon in Route 1, Pikachu has gained 8 levels toward the target of 10.
Right, it's tracking its own progression.
It wasn't keeping that in its active context window. That would have blown past the token limit in minutes. It was offloading its working memory to the repo.
And the critical part is that after its context window was intentionally reset to simulate a new session, the agent would wake up with amnesia, immediately read its own notes, and seamlessly continue multi-hour training sequences or complex dungeon explorations.
Just picks right back up.
This coherence across summarization steps is what enables long horizon strategies. It would be literally impossible if you were just trying to keep all the state, all the previous moves, and all the screen pixels stuffed inside the LLM's active context window.
This translates directly to enterprise software engineering. OpenAI described using this exact pattern. For small changes, the agent uses ephemeral lightweight execution plans. But for massive features, the agent creates complex execution plans with progress checklists and decision logs, and it actually commits them into the repository.
It writes it down.
The active plans, the completed plans, and the known technical debt are all versioned and co-located with the code. This allows a fresh agent to spin up, read the claude-progress.txt file, see that step 4 of 10 failed yesterday, and pick up right where the previous session left off.
And to drive a pull request to completion without constantly nagging human engineers, OpenAI instructs Codex to review its own changes locally. It requests specific sub-agent reviews, responds to its own feedback, and iterates in a loop until it is satisfied.
They jokingly call it the Ralph Wiggum loop.
Yeah, like the kid from The Simpsons saying, I'm helping, because the agent is essentially talking to itself, grading its own papers, and fixing its own typos locally before it ever bothers a human reviewer with a PR.
I love that. But practically speaking, if I'm a SCAF engineer, this is where my alarm bells start ringing.
Oh, for sure.
Even with perfect memory, and even with a diligent Ralph Wiggum loop where the agent checks its own work, an LLM is essentially a hyper-advanced autocomplete. It can and will confidently generate entirely wrong solutions.
Consistently.
It will hallucinate an API endpoint that doesn't exist, and it will write tests that pass precisely because it hallucinated the mock to match the hallucinated endpoint.
Yeah.
So if your agent is doing all this work autonomously, how do we actually know the code is good before it merges?
Which brings us perfectly to our third major principle, and perhaps the most important rule in the entire Dark Horse PRD, evaluator before generator.
Right.
Expanding a generator's capability without expanding the evaluator's capability just scales up error throughput. Think about it mechanically. If you give an agent the power to write 10,000 lines of code a minute, but your testing suite can only reliably verify 100 lines a minute, you aren't building a faster engineering team. You are just building a very fast factory that produces high-confidence garbage.
So we have to revisit the foundations of test-driven development, or TDD, and continuous integration. But I want to skip the basics. Our listeners already know what the red-green refactor loop is. They know you write the test, watch it fail, write the code, watch it pass. But TDD was designed for human engineers.
Yeah.
It assumes human laziness or human oversight.
Exactly.
AI doesn't have laziness. It has hyper-productive hallucinations. If your TDD loop isn't watertight, the AI will just write 5,000 lines of highly confident garbage.
Yeah.
So why do agents need TDD even more than we do?
Martin Fowler has a foundational analogy for this that maps perfectly to AI. He describes the concept of a mischievous imp. Imagine you have an invisible, mischievous imp living in your code base. This imp is able to make simple modifications to your code while you aren't looking like commenting out critical lines, reversing Boolean conditionals, or off-by-one errors in loops.
Okay.
Fowler argues that a sound, robust test suite should be so comprehensive that it would never allow the imp to do any damage without at least one test turning red.
And agents are exactly that. They are fast, incredibly productive, occasionally brilliant, but very often mischievous imps. Because LLMs can hallucinate with extremely high confidence, they need a fast, completely objective feedback loop. If the agent makes a change, it needs to know in seconds if it broke a downstream dependency. If you have a flaky test suite or a test suite that takes 45 minutes to run, you completely destroy the agent's ability to iterate.
So you need the classic test pyramid. Lightning-fast unit tests, integration tests for the database layer, contract tests to ensure microservices aren't breaking each other's APIs, and end-to-end tests. But in the context of AI factories, the Dark Horse PRD introduces a critical distinction that most traditional engineering teams don't have.
This is huge.
You must separate your tests into two distinct categories: visible harnesses and holdout harnesses.
I hear you on this, but let's play devil's advocate for a second. Managing one test suite is already a headache for most DevOps teams. Now we're talking about managing a duplicate, hidden test suite. That sounds like an absolute nightmare for maintenance. How do you maintain a hidden test suite without it constantly drifting from the main code base, and why is it so necessary?
It's necessary because of how LLMs optimize. This is a concept borrowed directly from machine learning model training. A visible harness is your standard test suite that the agent can see and run locally. It includes your unit tests, your linting rules, and public contract tests. The agent uses the visible harness to do its standard red-green refactor loop. But here is the massive danger. If an agent can see the tests, and its only goal is make the test pass, it can and will optimize its code specifically to pass those tests without actually solving the underlying business problem correctly.
It games the test.
It overfits to the visible harness. If the test checks for a specific string output, the agent might just hard code that string instead of writing the complex logic required to generate it dynamically.
It's the classic lazy AI problem. It finds the path of least resistance to a green checkmark. To prevent that, you must have the holdout harness. This is a private test suite that the agent absolutely cannot see or execute directly. It lives outside the agent's context and sandbox.
Completely isolated.
It might include adversarial edge cases, hidden contract probes, complex incident replay suites, and regression tests derived directly from production traces.
Right, so the workflow looks like this. The agent writes the code, runs the visible harness, sees all green, and confidently submits its pull request thinking it has finished the job. But then the continuous integration pipeline running on your secure build server runs the holdout harness.
The ultimate judge.
This determines if the agent truly solved the algorithmic problem or if it just gamed the visible tests. And as for your point about maintenance drift, You don't write the holdout harness manually. You use an agentic pipeline to generate holdout tests from real production traffic traces. The holdout harness updates itself based on actual user behavior.
And we have a perfect real-world war story of why this holdout evaluation is necessary. Anthropic published research on demystifying evils, where they talked about testing an Opus 4.5 model on a complex flight booking task. The static, visible evaluation was written to check if the agent booked a flight according to a very specific, rigid corporate policy.
Right.
But the model actually analyzed the policy, found a logical loophole in the rules themselves, and booked a flight that failed the static evaluation as written, but actually provided a significantly better, cheaper, and faster solution for the end user.
That anomaly is fascinating because it highlights the limits of traditional testing. The AI essentially said, your test is flawed, and your policy is inefficient. Here is a better way to do it. If you only had static, single-turn evaluations, you would mark that as a failure. But you actually want that kind of emergent problem-solving. It shows why static evaluations are insufficient for high-level agents. You need dynamic, multi-turn evaluations.
Let's define what a multi-turn evaluation actually looks like in practice. Anthropic defines it as an agent interacting with tools, a task, and a live environment. It executes an agent loop of reasoning, making tool calls, observing the result, and updating the environment.
It's a dialogue with the system.
Right. It might take 20 steps to book the flight. Then, an entirely separate grader model or script looks at the final working outcome in the environment to verify success, rather than checking the specific syntax of the intermediate steps.
Anthropic also makes a really important distinction for engineering leaders tracking metrics. You have to separate your capability evils from your regression evils.
Okay, break that down.
A capability evil asks, what can this agent do well at the absolute frontier of its intelligence? It targets tasks the agent currently struggles with, and ideally starts with a low pass rate, maybe 20%. This gives the engineering team a hill to climb. It's a benchmark for improvement as you tweak the harness or upgrade the underlying model.
And regression evils.
A regression evil, on the other hand, asks, does the agent still handle all the basic, mundane tasks it used to do flawlessly? These regression evils must have a nearly 100% pass rate. If they drop, you've introduced a regression in your prompt or your harness.
And when you're tracking these pass rates, you have to account for the inherent non-determinism of LLMs. Because agents use probabilistic models, their behavior varies between runs. You can give an agent the exact same prompt twice and get in two different approaches. Anthropic tracks this using a metric called pass@k. This measures the likelihood that an agent gets at least one completely correct solution in k attempts.
Exactly. If you have a score of 50% for pass at 1, it means the model succeeds on its very first try half the time. But if you increase K to, say, 5 attempts, allowing the agent to try, fail, and retry in a loop, the pass at K score will naturally rise significantly because the agent has more shots on goal to self-correct.
That makes total sense.
In a dark factory, you often tune your system to rely on high pass at 5 or pass at 10 rates. Because compute is cheap, and letting the agent retry 10 times in the background is faster than waiting for a human.
So if we need these dynamic multi-turn evaluations running in loops, this raises a huge infrastructure question. How do you run these complex evaluations safely? You can't just unleash an unpredictable agent on your actual production database to see if it can successfully resolve a simulated data corruption issue.
No, absolutely not. And this is where the Dark Horse PRD introduces the concept of the digital twin universe, or DTU. The DTU is a representative, highly controllable simulation environment for your services, workflows, data, and failure modes. It allows for high-confidence evaluation without any direct production risk.
The DTU isn't just a fantasy sandbox with fake data. It has to be close enough to real operational behavior that a pass in the DTU actually guarantees a pass in production. The DTU provides service doubles and mocks for external third-party integrations. It provides seeded, synthetic data sets that look structurally identical to production data but contain no PII.
That's crucial for compliance.
Very. It provides deterministic clocks so you can test time-based logic without waiting. And crucially, it allows for the replay of sanitized production traces.
Think about how powerful that is. If you have a complex NAN integration layer routing webhooks, the NAN nodes can act as the real choreography layer in your DTU, but the specific real-world endpoints like the actual Stripe API or the live Salesforce instance are swapped out for intelligent mocks that simulate the expected latency and failure rates. The agent operates in the DTU thinking it is in production, which means you get incredibly high-fidelity evaluation of its behavior.
Okay, let's take a breath and look at where we are. We have established that the environment needs to be fully legible via dev tools and observability endpoints. We've established that the repository acts as the absolute memory through progressive disclosure, ADRs, and structured notes. And we have rigorous, visible, and holdout evaluators backed by a digital twin universe protecting the mainline code base.
We've built the factory floor.
The next logical phase in building our factory is determining how we actually govern this system. Because right now, the agent is doing the work, but a human is still presumably clicking the merge button. When do we let the agent push code to production on its own?
This is where we get into the governance of risk-tiered autonomy. Principle 11 of the Dark Horse PRD is very clear, and it's something every engineering manager needs to internalize. Autonomy is earned, not assumed. You don't just upgrade your GitHub account, flip a switch on day one, and declare your repository a level 5 dark factory. You scale autonomy progressively based on explicit risk tiers and autonomy tiers.
Let's break those tiers down because this is a highly practical framework you could implement in your CI/CD pipeline tomorrow. Let's look at the risk tiers first, which define the blast radius of a change. The PRE defines these from R0 to R4.
Okay.
R0 is the absolute lowest risk. These are changes to documentation, re-RDM files, prompt templates, comments, or non-executing metadata. If the agent messes this up, the code still compiles and runs. R1 includes test files, internal developer tooling, low-risk syntactic refactors, and non-user-facing utility scripts.
Right.
R2 steps up the risk to banded feature work, internal product flows, and non-sensitive API integrations. R3 is user-facing production behavior, shared core library changes, and updates to the deployment pipeline itself.
Getting serious.
Very serious. And finally, R4 is the highest risk surface. This includes security configurations, authentication logic, secrets management, compliance-bound data handling, financial transaction logic, and destructive database migrations.
Now, those risk tiers map to autonomy tiers, which dictate what the agent is actually allowed to do without a human. These go from A0 to A5. A0 is effectively read-only mode. The agent can analyze the codebase and suggest changes in a chat interface, but it cannot autonomously open a pull request without explicit human approval.
Okay, so that's Copilot, basically.
Right. A1 means the agent is allowed to draft the changes and open the PR, but humans must conduct a full manual review and hit the merge button. A2 is where it gets interesting. A2 allows the agent to execute low-risk changes and auto-merge them, bypassing human review as long as all the CI gates pass on approved surfaces.
Wow, okay.
A3 enables self-review. The agent can submit a PR, receive automated feedback from linters and holdout harnesses, remediate that feedback autonomously, auto-merge on bounded surfaces, and trigger a deploy to staging or non-production environments.
That's a huge leap in productivity.
A4 allows autonomous deployment directly to production on eligible surfaces, but it requires automated rollback mechanisms and synthetic monitors to be in place. And finally, A5 is full dark factory mode. Humans simply provide high-level business goals and governance policies, and the system executes the entire routine cycle end-to-end.
The absolute ironclad governance rule here is that the autonomy tier must be constrained by the risk tier. For an R0 documentation change, you might allow A3 autonomy very quickly. If the agent wants to fix a typo in the reanim, let it auto-merge. But for an R4 security change, like updating the JWT validation logic, the system should generally remain locked at A0 or A1. A service only moves up in autonomy when the historical metrics support it, when the flake rate is low, the rollback rate is near zero, and the holdout pass rate is stable over hundreds of runs.
But if we connect this to the bigger picture, how do you actually enforce these rules? You can't just have these tiers written in a Google Doc that humans are supposed to remember during code review.
They'll forget on day 2.
Exactly. They have to be implemented as executable policy. This is governance as code. You use GitHub branch protections, required status checks, deployment protection rules, and CI concurrency limits. If an agent's pull request touches any file in an R4 directory, the GitHub Actions policy automatically intercepts it and requires a mandatory human review from the security team, regardless of what the agent tries to do or how green the visible tests are.
This fundamentally changes the merge philosophy of an engineering team. In a traditional human-first environment, requiring manual review for every single pull request is standard practice. It's how we ensure quality. But in an agent-driven system where Codex or Claude can generate dozens of pull requests continuously day and night, human review becomes a massive crippling bottleneck.
It defeats the purpose of the factory.
Exactly. If humans become the universal gate for every PR, the system's throughput advantage completely collapses. You're just creating a backlog of PRs that your senior engineers will grow to resent.
OpenAI explicitly noted this in their zero-code experiment. They found that as agent throughput increased, blocking everything at human review just didn't scale. They had to move to a model with minimal blocking merge gates for certain lower-risk tiers.
Makes sense.
In a system where agent throughput far exceeds human attention, corrections are cheap, and waiting is expensive. If an agent breaks an R1 internal tool, it's faster to let an automated monitor catch the break and have another agent instantly revert or fix it than it is to wait 24 hours for a human to review the initial PR.
But they offset this risk of auto-merging with intense policy enforcement and an artifact called the evidence bundle. This is crucial. The evidence bundle replaces the vibes-based trust of human code review. We've all reviewed PRs where we just skim the code, trust the senior engineer who wrote it, and hit LGTM.
Feel guilty.
You can't do that with AI. Every pull request or deployment candidate must have an attached artifact package generated by the harness.
What exactly goes into this evidence bundle? It is a structured JSON payload and markdown summary. It must include the trace IDs of the agent's execution path, the raw outputs of the visible and holdout evaluators, the explicit risk tier justification for why it believes it is allowed to auto-merge screenshots or headless video recordings for any UI-affecting changes, and the relevant ADR references that justify its architectural choices.
It's complete receipt of the work.
Exactly. A human, or more likely, an automated policy gate, can parse the evidence bundle and immediately see cryptographic proof that the change is safe, rather than having to read every line of generated code.
Let's give a highly concrete example of this in action, because this is where the magic happens. Imagine your system is set to A2 autonomy on an R1 risk tier. An agent is assigned a JIRA ticket to fix a bug in an internal data processing script. The agent spins up, reads irrelevant progressive disclosure docs, and creates an execution plan. It writes the code. It runs the visible harness locally, and the tests pass. It then packages the evidence bundle, which includes a complete JSON trace of every terminal command it executed to fix the bug. It opens the pull request. The GitHub Actions CI pipeline triggers. It sees the R1 tier flag. It validates the complete evidence bundle. It runs the holdout harness on an isolated runner, which also passes.
Flawless.
The CI pipeline then auto-merges the PR. The bug is fixed, tested, validated, and merged, completely bypassing human review, but doing so safely because the governance and evidence were bulletproof.
But let's play devil's advocate on security for a moment. What's fascinating here is how security and sandboxing play into this autonomy. In our example, we casually mentioned the agent executing terminal commands to run tests.
Right.
If you give an agent the ability to execute arbitrary bash commands on a server to build a project, you are opening up a massive, terrifying security vector, especially regarding prompt injection.
Oh, man.
If a malicious user submits a bug report that contains a hidden prompt injection asking the agent to read your SSH keys from the environment variables and curl them to an external server, a naive agent harness might just do it. It has the permissions, so it complies.
This is a huge concern. Anthropic tackled this exact problem with their Claude Code CLI tool. Their initial solution was constant permission prompts. Every time the agent wanted to run else or cat or npm test, it would pause and ask the human for permission.
That sounds exhausting.
It is. If the agent has to ask permission for 50 commands in a row, the human gets severe approval fatigue. The developer just starts blindly mashing Y and hitting enter without reading, which completely destroys the security posture anyway.
So Anthropic realized they needed to move enforcement from the human to the operating system. They introduced OS-level sandboxing using Linux Bubble Wrap and macOS Heatbuild.
This sandboxing is a technical marvel. It enforces two strict, impenetrable boundaries around the agent's execution environment: file system isolation and network isolation.
File system isolation ensures the agent can only read and write to the specific current working directory of the project. If it tries to CD out to the root directory or access the / folder, the OS kernel itself blocks the action. Network isolation ensures the agent can only connect to approved servers through a strict proxy. It completely blocks the agent from opening a socket and phoning home to an attacker's server.
And the results of implementing this OS-level sandbox were staggering. By defining these mathematically secure boundaries, Anthropic found they could safely reduce human permission prompts by 84%.
That's a massive UX improvement.
Huge. The agent is actually more autonomous because it knows, and the harness knows, that it is operating inside a blast-proof room. If a prompt injection attack tries to force the agent to step outside the sandbox, the OS blocks the execution at the kernel level and alerts the harness, terminating the session.
This sandboxing pairs perfectly with the Model Context Protocol, or MCP. NCP provides a standardized, open-source way to connect AI models to external data sources and tools. When you are integrating external tools via MCP, say, through a connector to a live production database or a third-party billing API, you can define explicit, granular approval gates.
Okay, so fine-grained control.
You can use the require approval parameter in the MCP schema to ensure that any sensitive actions, like executing a drop table command or sending an outbound email to a customer, always trigger a human approval flow. Meanwhile, safe actions like reading a public database schema or querying a local log file run completely autonomously.
So what does this all mean? It sounds like an incredibly elegant, beautifully well-oiled machine. You have the secure OS-level sandbox, the MCP integrations, the cryptographic evidence bundles, the risk-tiered auto-merging policies. But we all know that software is entropy. Machines break down over time. What happens when these autonomous agent factories run continuously for weeks or months on end without human intervention?
That brings us to our final major segment, and perhaps the most relevant for anyone who has actually tried to deploy these systems in production: the common failure modes of long-running agents and how we mitigate them.
This is where the rubber meets the road.
The most insidious, creeping problem in a long-running agentic factory is context pollution and the massive accumulation of AI slop.
AI slop. I love that term. Even though the reality of it is terrifying for a code base. We've all seen it. A junior engineer copy-pastes a bad snippet from Stack Overflow, but an agent operates at 100x the speed of a junior engineer. OpenAI experienced this firsthand during their zero-code experiment. They found that agents tend to relentlessly replicate local patterns that already exist in the repository, even if those patterns are uneven, deprecated, or suboptimal.
It just assumes the local code is the gold standard.
Exactly. If there is a slightly messy, verbose way a database call was made in one older file, the agent will pattern match that structure and eagerly copy that messy approach into 10 new files it generates. Over time, this inevitably leads to severe architectural drift. The code base becomes a tangled mess of hyper-local optimizations.
Initially, the human engineers at OpenAI tried to address this drift manually. They were spending every Friday a full 20% of their expensive engineering week just doing manual code reviews and cleaning up this accumulated AI slop.
Unsurprisingly, that did not scale.
Not at all. Technical debt is exactly like a high-interest loan. It compounds daily. You cannot let it accumulate and try to tackle it in painful manual bursts.
So their solution was to treat the codebase like memory and build garbage collection directly into the factory operations. This is Principle 10 of the Dark Horse PRD. Garbage collection is mandatory. You can't just have agents building, you need agents cleaning.
I like that framing. Building and cleaning.
They explicitly encoded golden principles into the repository's progressive disclosure docs. These are highly opinionated mechanical rules like always prefer the shared internal utility packages over hand-rolled helpers, or all error handling must submit to this specific telemetry endpoint. Then they set up background codex tasks on a regular automated cadence. These background agents constantly scan the code base for pattern deviations, flag outdated documentation, update the docs for freshness, and autonomously open targeted, bite-sized refactoring pull requests.
And because these automated refactoring PRs are small, focused, and backed by the holdout harness, most of them can be reviewed by a human in under a minute, or just auto-merged if they fall into the R1 risk tier.
They're beautiful.
It functions exactly like garbage collection in a programming language memory manager like Java or Go, but applied to codebase entropy. You catch and resolve bad structural patterns on a daily basis, preventing them from metastasizing across the repo.
Another major, incredibly frustrating failure mode for long-running agents is the one-shotting hallucination. You give an agent a complex, multi-part prompt. It works diligently for a few minutes, makes a flurry of changes across 15 files, and then prematurely declares the massive job done without ever verifying the end-to-end functionality. It just assumes its code works.
Anthropic observed this exact behavior when stress testing their Claude agent SDK. If given a high-level, ambitious prompt like, build a full-stack clone of Claude.ai, a naive agent would try to hold the entire architecture in its head, try to do too much at once, get completely tangled in its own context window, or just stop halfway through, hallucinating that it had finished the database schema when it hadn't even started it.
Just giving up, basically.
Yeah. To overcome this, they developed a brilliant deterministic two-part solution: the separation of concerns into the initializer agent and the coding agent.
Yes, the architectural separation here is key. You don't just use one massive swarm agent. The initializer agent runs only once, at the very beginning of the task, Its prompt is highly constrained. It asks it to set up the environment scaffolding, initialize the Git repo, read the architectural ADRs, and create that Claude progress.txt file we talked about earlier.
Setting the stage.
Right. But crucially, it is asked to write a comprehensive JSON file, listing all the specific feature requirements, say, over 200 granular features required for the app clone, and it must mark every single feature in that JSON file with a status of failing.
This creates a highly legible, deterministic roadmap. The initializer agent then terminates. Then the coding agent takes over. Its prompt instructs it to work incrementally and strictly forbids one-shotting.
It has to slow down.
It is only allowed to tackle one failing feature from the JSON list at a time. It reads the first failing feature, writes the specific code for it, runs the visible harness to test it, and only when the test passes is it allowed to change that one specific JSON status from failing to passes. Furthermore, it must make an atomic git commit with a descriptive message before moving to the next feature on the list.
Which is a lifesaver for debugging, because if the agent goes down a bad path on feature 47 and totally borks the app build, it doesn't have to guess how to untangle the mess. The harness can just use Git to revert the branch back to the last working atomic commit at feature 46. It maintains a clean state. But this raises a practical question. What happens when the coding agent is on feature 150 and its context window inevitably fills up with all the previous code, tests, and tool outputs?
This raises an important question about managing long-horizon workflows. When the context window reaches its limit, you need a mechanism to persist the intelligence and the state without losing the plot or dropping the context of the overarching goal. This is where the concept of compaction comes in. Compaction is a server-side process within the harness that monitors the agent's token usage. When a conversation nears the context limit, the compaction process pauses the agent. It takes the entire history, summarizes its critical contents, extracting key architectural decisions, pending tasks, and unresolved bugs, discards all the redundant, token-heavy tool outputs like raw terminal logs, and then reinitiates a brand new context window for the agent injected with that high-fidelity summary.
And beyond just compacting the main thread, you can use multi-agent architectures to keep the context clean from the start. Rather than having one massive agent trying to do everything and read every file, use an orchestrator worker pattern.
Exactly. Anthropic detailed how they built a multi-agent research system that avoids context bloat. The main orchestrator agent maintains the high-level plan and the progressive disclosure map. When it needs deep information, say, it needs to understand how a specific, undocumented legacy API works. It doesn't read the whole API itself. It spawns a specialized sub-agent.
A scout, basically.
Right. This worker agent goes off and explores extensively, maybe using tens of thousands of tokens to search the web, read API docs, and run test queries. But crucially, the worker agent does not dump all those raw tokens back into the main orchestrator's context window. It returns only a condensed, distilled summary of its findings. This separation of concerns prevents context pollution and information overload for the orchestrator, keeping it focused on the main goal.
Here's where it gets really interesting. When you combine all these primitives we've discussed today, the native tools, the legible hosted shell, the compaction, the orchestrator patterns, you get agents doing incredible, highly reliable enterprise work. OpenAI highlighted a case study with Glean, an enterprise AI search company. They built a complex Salesforce-oriented agent, but they didn't just give it a massive prompt. They used skills. Skills are versioned executable playbooks, often stored as a skill.md manifest, that are mounted directly into the agent's container.
By using these explicitly defined modular skills instead of relying on fuzzy, open-ended LLM routing, Glean saw massive improvements. They increased their agent's evaluation accuracy on complex Salesforce tasks from 73% to 85%, which is a huge jump in enterprise reliability.
Massive.
And because the agent didn't have to think as much about how to approach the problem, they reduced the time to first token by 18%. The skills act as living standard operating procedures. They encode the exact workflow, the guardrails, the required tools, and the data templates the agent must follow. It turns the agent from a creative, unpredictable guesser into a deterministic, reliable, governed worker.
And that is exactly what a level 5 dark factory needs to be. Reliable, deterministic, governed. It shouldn't rely on the emergent creativity of an LLM to figure out how to commit code. The environment should dictate that path. So let's wrap up this deep dive. Our core thesis today has been that in the rapidly accelerating age of AI software development, frameworks are transient. The specific orchestrator you use today will likely be obsolete in a year. But the harness, the evaluators, and the repo as memory, those architectural concepts are permanent. Building a level 5 dark factory requires treating the environment with as much respect, rigor, and engineering effort as you treat the AI model itself.
To summarize our key takeaways for the engineers listening, first, the harness is the judge, the agent is the worker. Stop obsessing over the generator model and focus your engineering effort on building the evaluation environment. Second, the repository is the memory. Ephemeral chat contexts don't exist to an agent. Progressive disclosure and immutable ADRs must entirely replace human tribal knowledge. Third, evaluator before generator. Do not scale your agent's ability to write code without equally scaling your system's ability to test it with both visible and private holdout harnesses. Fourth, risk-tiered autonomy. Move from simple R0 drafting to autonomous R3 production deployment based on strict cryptographic evidence bundles and policy as code. And finally, garbage collection is mandatory. You must build automated background loops to clean up AI slop and prevent architectural drift.
So, with all that said, what should you not build first? Do not start your AI journey by building a monolithic, highly abstracted, multi-agent swarm tied deeply to a specific hyped framework before you have a working, rigorous evaluation environment. If you build the generator before the evaluator, you are flying blind and just scaling up tech debt. Do not try to stuff a massive instruction manual into a single agent.md file. Please, do not rely on complex agent theater when a simple deterministic script or workflow would suffice.
Instead, here's your concrete checklist of what you can actually try next when you get back to your keyboard. First, audit your repository's legibility. Run an experiment. Can an agent easily read your UI state, your server logs, your PromQL metrics, and your test outputs via API calls without a human having to copy-paste anything?
That's step one.
Second, restructure your agents.md file. Strip it down, make it act purely as a short table of contents, a map pointing to modular markdown files in a docs directory. Third, implement a visible harness of standard unit tests and take the time to build at least one holdout harness that the agent cannot see to prevent it from overfitting.
Don't skip the holdout harness.
Fourth, define a strict evidence bundled JSON schema that your agents must attach to every pull request, including their trace IDs and evaluator results before CI will even look at it. And finally, investigate adding OS-level sandboxing, like Linux bubble wrap, to your agent's execution tools. Eliminate permission prompt fatigue while maintaining total kernel-level security.
It's an entirely new paradigm for software engineering, and the leverage it provides to small teams is truly unprecedented. But it requires immense discipline in the scaffolding, not just cleverness in the prompting. Which brings us to a final provocative thought for you to mull over as you design your own systems. We've established today that evaluators must judge the generators. You need robust holdout test suites to ensure the AI is writing good code. But as your systems scale and human engineers step further back, your agents will inevitably become responsible for writing the evaluation tests themselves. When the AI is both the student writing the exam and the teacher grading the exam, how will you, the human, verify the verifier? Thanks for joining us on this deep dive.